These are notes about what we did in class today. Since we had a short schedule, we didn't get to everything, so I thought I would put together some notes about what we did and what we didn't do. So we're in the unit called Impulse and Momentum, and it all started with throwing eggs. When the egg was thrown, it had a speed, and by various methods, whether it was a catch or hitting the sheet or hitting the table, the egg came to a stop. So all those cases I'm calling a catch in quotation marks. And the egg went from moving to not moving. In each case, this was because a force was applied to the egg, and this force was applied over a certain period of time. And so the egg went from not moving to moving in a certain amount of time, and we call that kind of a concept, we call it acceleration. So the egg was accelerated, it came to a stop because of a force, and that's an application of Newton's second law. So that's going to be our starting point. So Newton's second law, net force is equal to mass times acceleration. If we substitute change in velocity over time for the acceleration, we get this expression. And then we can multiply both sides by the change in time to give net force times time on the left and mass times change in velocity on the right. And then if we expand the change in velocity part, we get an expression like this. And if we distribute the mass to both of those velocities, we get this expression. So net force times time on the left is equal to mass times final velocity minus mass times initial velocity. So for the derivation, I had net force times time equals mass times change in velocity. The reason I had net force is because we started this from Newton's second law. But we usually consider forces individually when we're looking at how momentum changes. There may be more than one force acting on an object, but we consider them individually. So I've dropped the sigma to show a force times the amount of time it's applied results in a change in velocity for an object. The right-hand expression, mass times change in velocity, can be thought of as matter in motion. Mass representing the matter, change in velocity representing the motion. The quantity on the left is called impulse, and the quantity on the right is called change in momentum. We use the capital letter J for impulse and the lowercase letter p for momentum. And on this slide, since it's change in momentum, we have the delta character in front. The units for impulse are newtons times seconds. So the dot between means multiplication. The units for momentum are kilograms times meters per second. These units are equivalent to each other. Since impulse is equal to change in momentum, the units for impulse and the units for change in momentum, although expressed differently, are equivalent to each other. So we have several different expressions for change in momentum. This is the one we saw on the previous slides. Change in momentum is equal to mass times the change in velocity. If we expand change in velocity, we get this expression. And then distribute the mass, results in this. Now each one of these terms is a momentum. It's mass times velocity, both times. The first one is mass times final velocity, and the second one is mass times initial velocity. So the first one represents the final momentum, and the second one, the initial momentum. And so we end up with change in momentum is final momentum minus initial momentum, which you probably had guessed already because it's change in, and change in anything is the final value minus the initial value. So now let's look at some example problems. The first problem we did in class, but I'll recap it here. A woman runs a certain distance in a certain time, and we're to find her momentum. Her mass is given as 56 kilograms. The distance or displacement is 1.5 kilometers, and the time is 5 minutes. We don't use minutes and kilometers in physics, so we have to convert both of those. 1.5 kilometers is the same as 1,500 meters, and 5 minutes is 300 seconds. Question is, what's the momentum? So lowercase p equals what? I'm using guess and check, so I've written down the givens, I've written down the unknown. The next step is to write down an equation that brings all that together that can help me solve for the unknown. And the one that applies is momentum is mass times velocity. The problem is we don't have the velocity as one of the given pieces of information. But we were given displacement and time. And we can make use of the fact that velocity is displacement over time, substitute that in place of the velocity, and the result is this equation. Momentum is mass times displacement over time. Substitute the values and calculate, and this results in a momentum of 280 kilogram meter per second squared. The next problem is asking us to find the impulse needed to stop an object. The mass and the speed of the object are given. The mass is 32 grams, but in physics we don't work in grams, we use kilograms, so we have to convert that, and it is equivalent to 0.032 kilograms. The initial velocity is given as 38 meters per second, and we're trying to bring this object to a stop, so the final velocity will be 0 meters per second, and we're asked to find impulse, so capital J for impulse. What is that? So looking at the given information and what I'm trying to find, I see that a good equation to start with is impulse is mass times the change in velocity, final velocity minus initial velocity. And it's already set up. I don't have to rearrange or anything. Just substitute the values, and this is what the substitution looks like, and the result when calculated is negative 1.2 Newton seconds. The negative sign signifies that the force that was applied, or the impulse that was applied, was in the opposite direction of the motion. We assumed, implicitly, that the object was moving in the positive direction, so the impulse required to stop it would naturally be in the negative direction. The next problem is about a golf ball being hit by a golf club. The mass of the ball is given, and the velocity that it leaves the club face with was also given. The average force exerted by the club is given, and the question is, what was the time of impact between the club and the ball? So those given values were mass of 60 grams, which is the same as 0.06 kilograms. The initial velocity wasn't stated, but we know from experience that a golf ball being hit by a golf club starts at rest on the tee or on the ground. And so the initial velocity is 0 meters per second. The final is given as 75 meters per second. The average force is given as 3 times 10 to the 4th newtons, and we're asked to find the time of impact. In other words, the amount of time over which that force was applied. A good equation that makes use of the givens and the unknown is this equation. Force times time equals mass times the change in velocity. Rearranging to isolate the time variable, I divide both sides by the force, and it results in this. Substitution of values and calculation yields this result of 1.5 times 10 to the negative 4th seconds. That's a really short amount of time. To get a feel for it, move the decimal 4 places to the left, and that results in 0.00015 seconds. That's a really short amount of time. The next problem is giving a certain amount of force needed to stop an object, and we know the speed of the object. We also are given the amount of time required to bring the object to a stop, and we need to find the mass. So the givens are force is negative 452 newtons. The final velocity, since we're bringing the object to a stop, is 0 meters per second. The initial velocity is given as 155 meters per second. The time required to bring it to a stop is 19.2 seconds, and we need to find the mass. So once again, it looks like this might be a good equation to use. Rearranging to solve for mass, I have to divide both sides by the change in velocity, so that results in this. Substitution of values, and then calculation reveals that the mass of the object is 56 kilograms. And the last problem is about a pellet that travels at a speed and then it embeds itself into a pumpkin. And we're asked to find the average force exerted by the pumpkin to stop the pellet. So the given information is the mass of the pellet is 0.001 kilograms. The initial velocity is 100 meters per second. It comes to a stop in the pumpkin, so the final velocity is 0 meters per second. We're told how far it embeds into the pumpkin, 2 centimeters, which is 0.02 meters, and we need to know the average force. If you look at the equations that we have at our disposal, they all have time in them, so we're going to have to figure out what time is. So this is a good equation to start with, and I see that I need time. When I think about the kinematic equations that we have, none of them for accelerated motion, I should say all of them for accelerated motion, have acceleration in them as well. So I'm going to have to find the acceleration also. I'm going to have to get the acceleration to find the time, and then use the time to find the average force. This problem is a little bit more complicated than the rest, so just kind of follow along with me. So first stop, let's find the acceleration. We need an equation from kinematics that does not have time, and this is the one to use. Final velocity squared is equal to initial velocity squared plus 2 times the acceleration times the displacement. Rearranging to solve for acceleration gives this expression. Substitution of values and the calculation for acceleration gives a whopping 1250 meters per second squared in the negative direction. That result might look a little off, like surely it can't be that big, but look at the mass of the pellet. It's a teeny tiny mass, and so you're probably going to have a big acceleration. Alright, next stop, let's find the time. Now that we have the acceleration, we can use the definition of acceleration, change in velocity over time, because we have the velocities. And now we have the acceleration, so we can use this to find time. Rearranging to isolate the time variable gives this, and substitution of values and calculation gives the time of 8/100ths of a second. So this pellet embedded itself into a pumpkin 2 centimeters, and that took 8/100ths of a second. Okay, so now we found the time and the acceleration. We're all set. We can now find the average force. So this expression is the one that I originally wrote down but rearranged to solve for force. I know everything on the right hand side, so I just substitute those values, calculate, and I end up with a force of 1.25 newtons in the negative direction. Hopefully this helps. If you need to replay, do so, and pause wherever you need to look at the work or or to replay information.